Because while I won't be physically present with you, oh, I will be present. So, make a note you have your headphones too. Okay, so here's what we're going to do. We're going to write a logistic function. Given is the initial value is 25/4. The limit to growth, remember this is vocabulary that's used with logistic functions. And we contain the point 3, 50, 29. Okay? Now remember the general format. You're doing a logistic function, the format we're using, and there are other variations of it, particularly ones with an E, which the BFF you memorized had an E. But these are easier, so this is the easiest way to do it, so we're gonna set it up like this. This is what we're shooting for, that's what we're given. All right, so who remembers how we start this? What makes sense to start? Sam?
Put the 10 on the top.
The limit to growth is this number right here. And remember, graphically, the limit to growth is the top asymptote. So if you were going to graph this, you'd have your horizontal asymptote at 10. That's like the ceiling, the cap on it. So we already know our equation is 10 over 1 plus BC to the x. Okay? Now, where do we go next? There's like 3 variables we're solving for, A, B, and C, so it's like a 3-step process. A is taken care of. All right, now, where do we go? Initial value. Now remember, whether it's an exponential, Maria, or whether it's a logistic function, the initial value is like the y-intercept. It is the value of the function when x equals 0. Normally with these things, x is a time, 5 years, 8 minutes, whatever. So if x is 0, if time is 0, then this is the initial value. This is the starting point. Now, that is the point, x is 0, y is 25/4. So we're going to plug that in here. So 25/4 equals 10 over 1 plus b, c to the 0. We're putting in 0 for x, 25/4 for y. Okay, Patty, what are you doing, honey? Let's put that away. Okay. And here we go. Right? Now, what's the good news? C to 0 just disappears, right? Because it's 1. So we have 25/4 equals 10 over 1 plus b. Now what? How do you solve that? Cross multiply. So 25 plus 25b equals 100. So 25b equals 75, and it looks like b equals 3.
Wouldn't it be?
Oh.
It's not, it's 10.
Oh my goodness.
Actually, it's 40.
What did I do?
You put
4 times 10 is 40, and then you just kept it as 10.
I don't know what I did. It should be 40, right? Is that better? So 25b equals 15. And b equals, oh, that's not so great. B is what? 0.3 fifths. Okay, is that better? Okay, is that all right? So now we know we can go back up here and say, okay, now we know what b is. So we have 10 over 1 plus 3/5 c to the x. One more thing to find, we have to figure out what c is. What are we going to do to do that? Put in the other point that we have. So we're going to do it basically exactly the same thing. We're just going to put this point in instead. And know we have to solve that, right? So what are we gonna do? Cross multiply again. We're gonna do it, I mean, it's exactly what happened here. We're gonna cross multiply, so we have, I'll see if I can do it right this time. Keep an eye on me, because you know I'm a little crazy this morning. Does that look okay? So I'll subtract 50. Oh, that works out nicely, doesn't it? I got 2 for C. Everybody okay? And that means in the answer blank, I'm going to write my final answer. That's all one big problem. My final answer is going to be y equals 10 over 1 plus 3/5 times 2 to the x. Putting in the A, B, and C that I have found in my different steps. Alright? Okay, well, we did one like that yesterday. Just want to do another one so you get a couple of examples. There's some in the homework, those of you who have started looking at the homework. There's some in there. Speaking of looking at the homework, let's look on page 297 at problem number 31. So we're on 297. And we're looking at problem number 31. It's a little word problem. And the headline there, the red, says exponential growth. So 31 is an exponential problem. Let's see if we can figure it out. The population in 1890 was 6,250. The population increases at a rate of 2.75% per year. All right, stop right there. Can you write the equation that represents that problem? They gave me a starting population and they gave me a rate of increase. Can you write an exponential function that describes that? Now, think about what we talked about yesterday. We talked about, I don't remember, of course, the exact equation, but we talked about an equation that looked like this. What did we say about that equation? There's 2 numbers in it. There's a number here and there's a number here. What do those numbers represent in terms of the equation? 100 is the initial value. So this is the value. If you put a 0 in here for x, that goes away and leaves you with 100, right? It's the initial value. So if this were a population problem, it means we're starting with 100 people. Now what does this number tell me? How much I'm increasing by. Remember, we can have growth or decay. Did we talk about this yesterday? And when you're multiplying by a number bigger than 1, that means you're adding 1 extra, you're growing. How much is this one growing by? 5%. So this is a 5% growth. If we were multiplying by 0.95 to the x, that would represent a 5% decay. However much you're more than 1 or less than 1 is your growth or decay. This is your initial value. Now, does that help what question you had, or do you have a different question? Okay. Hey, let me finish this problem and I'll get it, okay? So when I write my equation on my exponential, which is of this form, this represents the initial value, the number of people, the amount of money, the number of bacteria, whatever it is, that's your initial value. And then this tells you how much you are either increasing or decreasing. Now, with that in mind, do problem 31. what is that equation going to be for problem 31? What's my initial value? 6250, was it? Yep. And then, what am I multiplying by? Is my population increasing or decreasing? Increasing. So it's going to be 1 plus whatever I'm increasing by. So what am I multiplying by? 1.0275. Is it a 2.75% increase? So that's the decimal. So this is the equation that is going to apply to this problem. It's that easy, guys. It's that easy. Your initial population multiplied by your growth or decay. Now, first question says, that's the equation. Estimate the population in 1915. All right, so what are we going to do? If we want to know the population in 1915, how are we going to use this equation to do that? Plug what in for x? 25. Why am I plugging in 25 for x? Because 1915 is 25 years after the initial value, right? So that's why we're putting in 25 for x. X is the number of years past, and so it's 25. Now, please keep in mind, this is a population problem. When you type that in, you're going to get some wacky decimal. Let's round it off to the nearest person, so we don't have, decimal people. So whatever it is, round it off to the nearest person, that would be the answer. And my book actually has the answer in it, and it says 12,315. Okay? Now how would you do the second part of that problem? It says, how about 1940? Wouldn't you do exactly the same thing? But the exponent would be 50. No difference. You just change the exponent and move on. Okay, you got that? Now let's look at question B, because it's a little bit different. Predict when the population reached 50,000. So this is the equation we're using. That's the equation for this problem. But now we want to know when the population will be 50,000. What am I going to do now? Put 50,000 in for y. Very good. Now let's look at that for a second. Does that make sense to everybody, first of all, that the 50,000 would go in for y? Any idea how we go about solving that problem? Step 1?
Divide 62.
Yep, divide by 6250. So what's 50,000 divided by 6250?
8.
8 exactly?
Yeah.
Oh, that's perfect. That's wonderful. That doesn't usually happen, but we'll take it. So step 1 is always divide. Now, if it had come out, if the problem had been 8 equals 2 to the x, then life is perfect, and we would know the answer is 3. But we're supposed to figure out what power of 1.0275 8 is. Well, we could do trial and error, but it would take us a week to do that. Do you remember how you solve for an exponent when the bases don't match, when you can't do something like this? You use logarithms. So we're going to take the logarithm of both sides of this. Now, if you would prefer to ln both sides, no problem. Doesn't make a single bit of difference. I log unless there's an e in the problem. That's my personal choice. You can ln all the time. You can log all the time. Doesn't matter. Why did we do that? What's the beauty of that?
Gets rid of the exponent.
How does it get rid of the exponent? It doesn't get rid of the exponent, it moves the exponent. As soon as you take the logarithm of something to a power, the exponent can come out in front. Remember that? That's one of your properties of logarithms. Hollis and Ludington would not be proud at this moment, people. The exponent comes out in front. So we have log 8 equals x log 1.0275. The beauty of taking the logarithm of something to a power is it's no longer a power, it becomes a coefficient. So now to figure out what x is, it's a simple division problem. Do you see that? Now, one word of caution, if you haven't done, typed in logarithms in a while, most of your calculators, when you type log, are automatically going to put a parentheses there. I mean, it'll come up log parentheses. After you put the 8 in, close those parentheses before you do divided by. So log 8 divided by log 1.0275. And I'm going to round that off to about 77 years. It's a little bit less than 77. It's 76.65. Is that what you got? But just to keep it simple, I'm going to say 77 years. Now be careful though. What does the question ask? Yeah, it says in what year, okay? So this tells me I have to wait 77 years, but when did I start? When was the initial value? 1890, so the answer would be 1967. Actually, because it was a little less than that, it would be sometime during 1966, because it was actually a little bit less than that. All right, we're going to do another one of these, but before I do, I want to get to Maria's burning question.
It was on the homework, but I was just sort of confused.
What page? On this very page?
No, on 286.
286.
Like number 3, I thought you said the initial value was 5, but in the back of the book it says it's 1.
Oh yeah, no. If your equation is y equals 5 to the x, remember exponentials are y equals a times b to the x, and a is your initial value. A is not the thing that has the x on it, that's b. So here, I don't physically see an a, I see b to the x, so my a must be an understood 1. So the initial value is 1. Does that make sense?
Yeah.
Okay. Yeah. This is your initial value. And then this is your base. And the base is what tells you how you're growing. This thing is growing really fast. That's like 500%, so it's growing really fast. Okay? All right. Glad we got that taken care of. Let's go back to our page now. And I'd like you to try 32 with your partner. It's exactly like the one we just did, different numbers, of course. I want you to do the first part of A, and I want you to do B.
Just the first part of it?
Just the first part of A. The second part's exactly like the first part, so we won't waste our time. But we're going to do 32, problem 32, the first part of A, and then B. And if I have someone who would be willing to put that up on the board for us.
297.
This is on page 297, problem 32, A and
No,
B.
because that's the year. Your initial amount is number 50.
And for A, we're only doing 1930. What equation are you using? Let's make sure we're using the right equation. 4200.
And then 1.0225
Yep.
dx.
So your equation should be 4200, 1.0225 to the x. Everybody should be using that equation to solve these two problems. So if you think you got one of them figured out, please come up and put it on the board for us. For problem A, does everybody understand why Taylor used 20? Why'd she use 20? The initial value was 1910, and we were wondering about 1930, so that's a 20-year span. She rounded off to the nearest person, okay? Anybody out there feel confident about B?
Can you check mine first?
Sam, you have it right. Sam, you have it right. I can do mine real quick. I have it. Look at this, come over here.
Jay?
Can I ask you a question?
Yeah, you're right.
Homework question.
Yep. In a minute. Let's get these done first.
Miss Ford, I have a question. Once you get your number, how do you get the date?
What date?
Like, the answer's like not a number, it's like a date. No.
Let's see what she does here. You're talking about her problem?
Yeah.
Let's see what she does here. Okay, so once again, Sam put in 20,000 for her Y value. Do not, I know when you look at this equation, you see X up here as a variable, and unless you can get a common base, the only way to solve for an exponent is use logarithms, okay? But don't jump in with the logarithms until you divide by this first. It's not going to work if you don't divide by that first. And that's going to happen in all the problems we do. You're going to have to do that division every time, because every exponential almost is going to have an A value, and you got to get rid of it. So she divided. Okay, and came up with, her answer was about 70 years. You get X equals 70 approximately. And so she said 70 years from the beginning, Caitlin. And the beginning was 1910, or no, 1930? Or 1910? What was the beginning?
1910.
1910. So the beginning was 1910. If we wait 70 years from 1910, we will be in 1980. That's how you get that answer.
Your 5 looks like a G.
What?
I said her 5 looks like a G.
Sorry.
All right, now before I get another homework question, I want to skip down and look at number 40. I want to look at number 40 because it uses the exact same principle, except instead of growing, we are decaying. So in number 40, we have an equation that looks like this. And I don't have to write my own equation, it just gives it to me. It says, the amount I have after T years is given by this equation. Okay, so this, I'm not writing my own equation. They're giving me this equation and saying, this is going to tell me how much stuff I have after T years. So if I wanted to know how much I had after 10 years, I would just plug 10 in, right? But that's not what it says. It says find the half-life. You know, wait a minute. What does half-life mean? Okay, so now your chemistry teachers aren't proud. What does half-life
It
mean?
means you have to find what the T is when C equals 7. Right?
Now why would you say when C equals 7?
Because the half-life of 14 is 7.
Aye.
Okay, now wait a second. This is carbon 14. I don't have 14 grams of it. How much of it do I have? Look at your equation. What's your initial value in this equation? 20. I have 20 grams of this stuff. So if I'm talking about half-life, then how much of it do I want to have? 10. So I'm going to put 10 because I got 10 grams of the stuff. 10 grams of it because it's starting with 20 and I want to know how long it takes, what's T, to get me down to 10. If I started with 14, Mallory, you're exactly right. I would want to end up with 7. But carbon 14 is the name of the thing, not the amount of it. All right, so I need to solve this. So what am I going to do? Step 1, divide by 20. That's easy. Now I'm going to take the logarithm of both sides, and because the problem has an E in it, I'm going to ln both sides. Why? Because ln is the symbol for natural logarithms, and it means log base E. The base of the natural logarithms is E. And in a minute, you're going to see why it is easier to use ln if you have an E in your problem. Now, could you log this and get the right answer? Absolutely. You can log everything you ever do. You can ln everything you ever do. It's just sometimes one is easier than the other one. ln, natural logarithms, definition, log base E. While I'm doing that, it doesn't have anything to do with this problem, but I'm going to go ahead and say log is the symbol for common logarithms, and that is log base 10. And they're called common logarithms because our number system is a base 10 number system. We have 10 digits, 0 through 9. We're a base 10 system, so they're called common logarithms. They were the first ones invented because they did computation with numbers. Okay, all right, so there's a couple definitions for you probably ought to know. Now, back over here, we said we're going to ln both sides. All right, so I'm going to do that. So I have ln 0.5. Now remember, when you take the logarithm of something to a power, the power comes out in front. So I have negative 0.0001216 t ln e. This comes out in front, the entire exponent. Earlier it was just an x, same idea, bigger exponent comes out in front. Okay? Now this is why it's so nice to use ln. Get your calculator out and let's evaluate this real quick. We're going to do some more work here, but I want to show you why this is so cool. And some of you already know because I hear you talking about it. Do you know how to take the natural logarithm of e? Well, you have to hit ln. And then e is actually second ln. It's actually right above the ln key. So press second ln. It pulls up e. Press 1 because it wants to know what power. Hit equals. And what does ln e equal? These cancel out. ln e is just 1. cancels out every time. So basically, when I ln'd both sides, I knew this part was going to disappear, and all I was going to have left was my exponent. So t will equal ln 0.5 over negative 0.0001216. So we can type that in on our calculator. You don't need the lne part, it always drops out. I got about 5,700 years, was it? Yep, 5,700 years. Would you call this a stable element or an unstable element from chemistry class? Now think about that before you say that. Think about it. It takes it 5,700 years to decay halfway. I'd say it's pretty stable, right? The unstable ones that have are the ones that have half-lives of 10 seconds or something like that. Okay? One of my chemo drugs before my transplant had a half-life of 30 minutes. So for the 30 minutes, I was having to do all kinds of things because the drug was very powerful. But after 30 minutes, it had done what it needed to do, and I didn't worry about it anymore. Very unstable, very unstable. This one's very stable. Okay, let's try one more of these examples, and then we've got some other work we need to do. Let's try number 39, and then JA, I'm going to get your question, okay? So we're going to do number 39. It's another one with an E, but they give me the formula, so I don't have to worry about that. Okay, so this is giving me the number of bacteria at time t. I don't have to write my own equation. This is it. What's that 100? That's how many I'm starting with. So the question says, when will the number of bacteria be 200? So where am I going to put the 200? B. I want this to be 200. Step 1. Uh-oh, what's step 1 always? Divide. Always divide. Always divide. So we get 2. So this problem we just did over here, we were doing half-life. Now we're doing doubling time, right? Basically, we're doubling it. Okay, now what? Somehow log both sides. I'm going to ln both sides. And when I ln both sides, this cancels every single time. So basically I have this equation. So t equals ln2 divided by 0.693. Which is, gosh, about 1. Yeah. So what does that mean?
1 hour.
What's my time? Hours. Every hour, this population is doubling. It's like food poisoning. Anybody ever have food poisoning? Doesn't take long to get sick because those little guys are in there growing fast. Okay? All right. Jay, we got some other stuff to do here, but let's get your question. What page and problem number?
It was 286 and number 11.
286, number 11. Okay, I did 12 in class,
Okay.
so would you just match it up? I mean, it's exactly the same thing. Look at what I did with number 12. Then you're going to use the x's and the f of x's. Okay? So try to do it exactly like I did number 12. With number 12, I use the x's and the g's. You're using the x's and the f's. And you're going to do exactly what I did. Class, remember from yesterday, when they give me that table, they're giving me 5 values, 5 points. I only need 2. And which 2 did we say we should use? Well, you want to start with the one with a 0, and then the lowest, easiest one, which is probably the one with a 1. Yep, those are the best ones. All right, now I need you to look on page 308. I'm going to do some problems, but first I have to give you a little bit of background information. Yep. Which curve is this? Well, now your pre-cal teacher's disappointed. You guys have managed to disappoint a lot of people today. This is your exponential. So this is y equals b to the x. You memorized it as y equals e to the x, but it'll work with any base, okay? So I'm just going to say b to the x. Y equals b to the x. Now, if I wanted the inverse of that, the inverse, you remember that the inverse just switches the variables. So it would be this, right? That would be the inverse. Now, we need, as mathematicians, your calculator needs it, computers need it. You need to be able to write things as functions. Believe it or not, this is a function. But it would be very hard for you to put that into your calculator, because when you put equations into your calculator, don't they have to be y equals? This is a function. We're going to draw it in a minute, but I can't really put it into my calculator because the y is in the wrong spot. So some great mathematicians a long time ago, a man named Napier, said this is problematic. As computers or calculating machines were being developed, he said this is problematic. So he came up with a new notation for this equation. Instead of writing the inverse like this, he wrote it like this. These are the same equation. These two equations are exactly the same set of points, but this one now has y equals, so I can put it in my calculator. Or I can do calculations with it in function notation, f of x. Now, why am I telling you that? Because you need to be able to translate logarithmic expressions. For example, if I said to you, what's the log base 4 of 16? You need to be able to figure that out without a calculator. And it's easy if you remember that these two are the same. These are exactly the same. Then the log base 4 of 16 equals something would be the same as 4 to the y equals 16. These two are the same. These are the same equations. So if my base is 4 and my x is 16, then this is saying 4 to what power is 16? So the answer would be 2. The inverse of the exponential is the logarithmic curve then. This is your logarithmic curve. They are inverses of each other. They are reflections across the identity line. They are both functions. This is the point 0, 1. This is the point 1, 0. They are inverses of each other. Exponentials and logarithmic functions are inverses of each other. But every logarithm can be written in exponent form. So we'll try one more, and then I want to do some on that page. If we had the log of 100, what does that equal? The log of 100. Well, first of all, what base is on that? 10. Remember, LOG all by itself always means base 10. Now, use this idea and translate that. What is this in exponent form? 10 to the x equals 100. So 10 to the x equals 100. 10 to the x equals 100. So the answer to that question is also 2. One more, and we're going to look at the ones in the book. Solve that little guy. Well, now remember, what's the base on here? Oh, the base on this is not 10. What's the base on ln? E. So e to the 5th equals x. E to the 5th equals x. E to the 5th equals x. This is the single most important thing we're going to talk about all week. This is big. You're dead if you can't do this. Dead mathematically. E to the 5th equals x. And the answer is e to the 5th. E is like pi. It's an irrational number. We just leave it e. So the answer would be e to the 5th. Okay, let's look on page 308. We are going to zip through the first 24 of these problems. Yep. You might want to do this on a piece of paper because I'm sure I assigned these. We're just going to zip right through them right now. Whoa. Alright, here we go. Let's look at them. How about number 1, the log base 4 of 4? Now I'm going to go ahead and put an equals x on that because I want to know what that equals. You don't have to do that, but it helps me kind of visualize a little bit. What does this equal? The log base 4 of 4 equals what? Well, translate it for me. 4 to the x equals 4. 4 to the x equals 4. So what does x equal? 1. The answer is 1. Period. Number 2. Log base 6 of 1.
0.
Very good. Because what does this say? 6 to what power equals 1? Are you seeing it? 6 to what power equals 1? Well, what do you raise 6 to get 1? 0. The only thing you can do is raise it to the 0th power. Now, would it matter if this base had been a 7? No. Isn't 7 to the 0 still 1? In fact, if I were going to make like a general property, could I say that the log base b of 1, any base, will always be 0? As we go along, we might come up with some little properties like that. But the idea is the log base b, any base, the log of 1 is always going to be 0. Okay, number 3. Log base 2 of 32. Anybody got that one figured out? X has to be 5. Why does x have to be 5? Because this says 2 to the x equals 32. So the answer is 5. Number 4, log base 3 of 81. You got that one? 4. I heard somebody say 4.
Yeah.
I don't know if the rest of you are keeping up or not. The log base 3 of 81. to the x equals 81. Remember, you gotta do that. You gotta think that. Think that. You don't even have to write it down after you've practiced a few of these, but you need to at least think about it. So x equals 4. All right, number 5. Oh my, it's getting a little harder now. Log base 5 to the cube root of 25. Radicals do not live in logarithm land. We do not like radicals in logarithm land. So, a couple of days ago, we talked about this, and that's why we talked about it. Cube root can be written as an exponent. What exponent is the cube root? 1/3. So this is the log base 5 of 25 to the 1/3. Would you agree with that? Another way of writing the cube root of 25 is as 25 to the 1/3. Now translate this for me. 5 to the x equals 25 to the 1/3. Now don't say x equals 1/3 because these don't match yet, do they? But can we make them match? Yes, because 25 is 5 squared. So 5 to the x equals 5 squared to the 1/3. So 5 to the x equals 5 to the 2/3. So what's the answer to question 5? 2/3. X equals 2/3. All these need to be done without a calculator. And they all can be done without a calculator. Okay, well, I'm not going to have room for all that. Okay, number 6. Okay, oh my, look at number 6. We got all kinds of issues here. One is the radical, so let's get rid of that. Patty, see this 5th root right here?
Yeah.
Okay, how can I rewrite a 5th root? What exponent would represent 5th root?
1/5.
Yep. So this is going to be 1 over 36 to the 1/5. Now what about the 1 over? I don't like that either. 1 over, I could make the exponent negative. So log base 6 of 36 to the negative 1/5. Would that be okay? Now let's translate it. 6 to the x equals 36 to the negative 1/5.
So 6 squared.
You're going to need to rewrite 36 as 6 squared to the negative 1/5. So what is x going to equal then? X is going to equal negative 2/5. Perfect. Now, I wrote every single step. After we've practiced a few, you may not need to write out every single step like that, but it's perfectly okay to do that if you want to. Okay, so we have the log of 10 cubed. This is number 7. The log of 10 cubed. Okay. Now wait a minute. What's the base on that? 10. So translating the log base 10, translating 10 to the x equals 10 cubed. Obviously x equals 3. My property list up here, I'm going to add another one. The log base b of b to the nth will always be n. Look, the log base 10 of 10 cubed turned out to be what? 3. The log base 10 of 10 to the 4th will be 4. the log base 10 of 10 to the negative 1/2 will be negative 1/2. That's a property that you're welcome to use. Saves time. Okay, that was 7. What was 8? Log base 10 of 10, what's 10,000? 10 to the 4th. So problem number 8 has a base 10, understood, LOG always means base 10, and I rewrote 10,000 as 10 to the 4th power, so that I can see the answer to number 8 is 4. How about number 9? 5, because 100,000 is 10 to the 5th. How about 10?
5.
Number 10.
Negative 4.
Negative 4. Number 10, kid, says the log base 10 of 10 to the negative 4. That answer will be negative 4. Ooh, what about 11? One-third. One-third, exactly. It has a radical in it. Radicals do not live in logarithm land, people. So when you see the cube root of 10, you are going to rewrite it as 10 to the 1/3. The base on that is 10, so we have the log base 10 of 10 to the 1/3, which is just 1/3. Isn't that easy? Very easy. Okay, what about 12? Oh my. A little bit harder, number 12. Take it a step at a time. Don't try to just guess. What do we have in number 12? We have the log base 10 of 1/what? I am not going to write that radical because I don't do radicals and logarithms. They do not mix.
1,000.
So 1,000 to the 1/2. Right? Now it's 1/1/. So we'll make that
Negative.
the log base 10 of 1,000 to the negative 1/2. Now there will be kids at this point that say the answer is negative 1/2. No, no, no. You can't do that until these two numbers match. They don't match yet. So what do you want to do with that 10? Or with that 1,000?
10 to the 4.
You're going, oh, be careful, it's not 10 to the 4th, it's 10 to the 3rd. So we have the log base 10 of 10 to the what?
3/2.
Negative 3/2, and the log base 10 of 10 to the negative 3/2 is negative 3/2. So again, I did that step by step. Some of you are going to be able to do some of that in your head, and that's absolutely fine. All right, 13, we're switching bases, but do not be afraid. It is simple. ln cubed. What's the base on here? E. What's log base E of e to the 3rd? 3. The answer's 3. Period. What's the answer to 14? Negative 4. What's the answer to 15? Watch this now. You got a 1/, kids. We don't deal with 1/overs very well. So we'll rewrite it as what? E to the negative 1st. So now you have the log base E of e to the negative 1st. The answer is negative 1. That's number 15. The answer is negative 1 because you have the log base E of e to the negative 1st. The log base E of e to the negative 1st. What about 16? I don't don't care what your base is. If you're taking the logarithm of 1, your answer is going to be 0. Every time. Every time your answer is going to be 0. What about 17? One fourth. Why is it 1/4? She's exactly right. Why is it 1/4? No radicals in logarithm land. What does the 4th root represent in terms of an exponent? The 4th root is e to the 1/4. So you got the log base e of e to the 1/4. The answer is 1/4. And the last one in this section, oh my, this is a little tricky. I'm not going to write that radical. It makes me twitch. And when I'm doing logarithms, I don't want radicals. So what am I going to have down there? E to the 7/2. I have e to the 7th, but the square root is 1/2. Now I don't care for 1/, so I'll rewrite the 1/, as e to the negative 7/2. Now remember, ln is base e, so you have log base e of e to the negative 7/2. The answer is negative 7/2. Okay, we just did 18 problems. Are you starting to get the hang of that a little bit? Now, 19 through 24 look different. They look incredibly hard. But I'm telling you, they are incredibly easy. The answer is 3. And the reason that the answer is 3 is because exponents and logarithms are inverses of each other. So when you put them both in the same problem with the same base, and that's the key, the base has to be the same. But when you have an exponent expression and a logarithm expression composited with each other like a composite function, that cancels out and the answer is just 3. It's like what happened when you did the log base 7 of 7 to the 4th. That all canceled out and the answer was just 4. Log base b of b to a power, this cancels out and leaves you with just n. B to the log base b of n all cancels out and leaves you with just n. So you can do those problems on site. What's the answer to 20? 8. Number 21, 0.5. Don't forget, there's no base written there, but the base is 10. So the answer in 21 is 0.5. What about 22? 14. What about 23? 6. Your bases are e. E to the log base e of 6 is 6. What about 24? 1/5. E to the log base e of 1/5 is 1/5. Easy, easy, easy.
And why is number 23 6?
Because you have e to the log base e. And that all cancels out. Okay? Now, what I want you to do is look in your packet, page 2. And you all just want me to shut the heck up, and I will after we get through page 2. All right, just the front right now. Just the front of page 2. Oh, the back should look familiar. We've done that already. Page 2. Can you figure out, I didn't even number these problems, I just scribbled them down. But the first one there, number 1, take a moment, gather your thoughts, We have practiced this. You can do it. What do you think about problem number 1? You got a couple different strategies. Anybody have an idea on the answer? Three? If you said 3, you are exactly right. Now, I'm not sure how you got 3. There's 2 choices, 2 ways to get 3. One is to say, I don't know what this equals, I have to figure it out. And then translate it. So 3 to the x equals 27. Can you see x would be 3? So that's one option to do problem number 1. You could also, to do problem number 1, use this property right here and say you are asking me to find the log base 3 of 3 cubed. 27 is 3 cubed. So the log base 3 of 3 to the third would just be 3. Either way, the answer to problem number 1 is 3. It doesn't matter how you do it, whatever makes sense to you. All right, how about number 2? Believe it or not, it's exactly the same kind of problem. If you said 1/2, you are right. Now, some of you are just writing down 1/2. That doesn't work. You have to make sense of it. ln square root of e. First of all, it makes me shake just writing that because I don't do radicals with logarithms. So I'm going to think of that as e to the 1/2. Now, what's the base here? So this is the log base e of e to the 1/2. The answer is just 1/2. We shouldn't need to think about that too much. What about number 3? 3. What about number 4? 0. The log of 1 is going to be 0 no matter what the base. Okay, 1, 2, 3, 4, 5. What about number 5? You are amazing if you said 2/3. I would have to go through a couple steps in my head or write them down. Cube root of 25 is 25 to the 1/3, right? 25 is 5 squared. So I have the log base 5 of 5 to the 2/3. So that's how we got the 2/3. That was my thought process. I'm not sure what yours was, but it was right. If you got 2/3, you did it right. How about 6? -5. 1 over means to the negative power. So we have the log base e of e to the -5th. Now don't get freaked out in the next one. Don't get freaked out. Cover up the 2 for a minute. What's the log base 4 of 4? 1. Kids, the log base 4 of 4, oops, I erased one of my properties there, but the log base 4 of 4, that's like the log base 4 of 4 to the first. So the log base 4 of 4 is just going to be 1, and then you're timesing that by 2, so the answer is 2. Something else you could do is the reverse of what we talked about before. Remember when we had the log of, x to the 8th, and we said we could pull this exponent out in front? When there's a number out in front of a logarithm, if you want, you can move it back as an exponent. So that would be the log base 4 of 4 squared. The answer is 2. A, is this an increasing or a decreasing problem? Is it a growth or a decay problem? It's an increase, it's a growth problem. And what's the percentage growth? 22%. This guy is growing 22%. What's the 0.813 out there? That's your initial value. So whatever we've got in this problem, we're starting with 0.813 of it. All right, and then take a minute and simplify that last thing. We're simplifying exponents. There's not a logarithm in it. Don't get freaked out. You're just simplifying it. Take a minute and do that. We'll see what you come up with. You got this done, Taylor? You already have it done? Good work. All right, what'd you do first? Okay, now remember, lots of things have to be done. There's no particular order. So she said, I got a negative exponent, so I'm going to turn this fraction upside down. Now, when you turn it upside down, everything stays exactly as it is. So this comes down, this comes up, nothing changes, except that becomes positive. All right? Maura, what'd you do next? Or what would you do next?
I squared everything.
She took everything to the second power, and that does include the numbers. So that will be 9x to the 8th, y to the 6th, over 4x to the negative 6th. Again, you don't have to do it in this order, but that has to be done. At some point, we have to do that, so she's got it done. Okay? Peyton, what did you do next? Or what would you do next if you were at this point?
I took the 6.
You have a negative exponent here. He has to go to the top. Does the 4 go to the top? No. So we have 9x to the 14th, y to the 6th, over 4, x to the 14th, because there's already 8 of them up there, and I'm bringing 6 more up. Everybody good with that answer?
Yeah.
Okay, now, I see you tomorrow, right?
Yep. Yeah.
Okay, tomorrow we're going to have a little quizzy quiz. Now, what do you think I'm going to quiz you over? Remember those 24 problems we just did straight out of the book? You're going to have to do not 24 of those, but a few of those. Okay? Everybody clear on that? All right, I'll see you tomorrow. Have a great day. Good doodling. Oh my gosh, we're doing logarithms. No time for doodling.